korunmuyor mu? Şey değişiyor. DNDV
Sure.
sıfır değil. DNDV ikisi de sıfır değil.
No.
DV sıfır.
You see, for delta n, you see, this is the number of forward reactions. Delta n A is equal to minus nu A delta n. Delta n B is minus nu B delta n. Delta n X is nu X delta n. And delta n Y is nu Y delta n. Delta n being the number of reactions in the forward direction. It can be negative also. Other questions? Okay, so let's look at bosonic systems in more detail. Now, for a fast review, if you remember, we defined a Q potential, which was logarithm of the grand canonical partition function, and this Q potential turned out to be PV over KT. And this grand canonical partition function was sum over all microstates of e to power minus beta E minus mu n. And remember, Ni, the occupation numbers, uniquely specify a microstate. If we ignore the interaction between the particles, E was equal to sum over Ni epsilon I, summed over all the single particle states. And capital N is sum over Ni. And then the Q potential became sum over each one of these Ni's from 1 up to infinity, well, 0 to infinity. It's a bosonic system. I can have infinitely many particles in the same microstate of e to exponential sum over I, minus beta, sum over I and I epsilon I minus mu. Mu is the unique chemical potential. I don't have a chemical potential for each microstate. Mu chemical potential in equilibrium is the same for all subsystems, just like the temperature is the same for all subsystems. So this we wrote as the product over I of sum over from Ni from 0 to infinity exponential of minus beta epsilon I minus mu Ni. Well, I can carry out that sum. It is just 1 over 1 minus e to power beta epsilon I times Z. This is my Q potential. Now this is the grand canonical partition function. The Q potential, which was the logarithm of this Q, this is just sum over minus the sum over all I of the logarithm of 1 minus Z e to power beta epsilon minus beta epsilon I, where sum over I is sum over single particle states. Z is defined as e to power beta mu. And we had also shown that the number of particles is equal to sum over I and I, which is sum over I 1 over Z to the power minus 1 e to power beta epsilon I minus 1. This is the total number of particles. So the task will be, from this equation, from the expression of the number of particles, solve for Z from here, solve for Z which will be a function of n, v, and t. N is, well, the left-hand side depends on n. T is, well, in e to power beta epsilon I, there is a t, beta, and it depends on v because epsilon I depends on v. So once you solve for z in terms of n, v, and t, put it over here. This is PV over KT. So if you put it over here, you get the equation of state. Well, if you want to calculate the energy, this will be I epsilon I and I, sum over I, epsilon I over Z inverse e to power beta epsilon I minus 1. Put it over here, you get the internal energy in terms of N, V, and T. Once you have the internal energy, take the derivative with respect to temperature, you get the specific heat, the heat capacity at constant volume, and, well, you can just calculate whatever you want. So the most difficult part will be how can we determine Z as a function of N, V, and T. So let's study this function a bit. Play around. We will be playing around a bit. Now the first question I ask you, how does Z change with temperature? I will be playing around with temperature, maybe even the number of particles. So how does Z change as a function of temperature if I keep N and V constant? What can I say about this without even solving the problem? Well, this is my differential equation which determines Z implicitly. Let me take the derivative with respect to temperature of both sides at constant N and V. Now the left-hand side is N. Since I'm keeping N constant, that derivative is 0, is equal to minus sum over I. I have to take the derivative of the right-hand side with respect to beta, with respect to temperature. And remember, beta depends on temperature, Z depends on temperature. That's what I'm looking for, how Z changes with temperature. But epsilon I are independent of temperature. They are the single particle energy levels. They only depend on the volume. So the derivative of the right-hand side will be 1 over Z to the minus 1 e to power beta epsilon I minus 1 squared. Now let me take the derivative of the numerator. Only the first term depends on temperature. So it will be minus 1 over Z squared del Z by del T and V e to power beta epsilon I. And then I have plus Z inverse 1 over KT squared minus 1 over KT squared e to power beta epsilon I. This should be equal to 0. Well, there's an overall minus sign. Let me just cancel those. You see, this term with this coefficient, they're all positive. So that term is a positive number. You see, whatever the temperature and the volume are, that term is positive. If you look at the coefficient of del Z by del T at a constant number and volume, well, everything that multiplies it are again positive. So it's again a positive number. So this should be 0, which basically tells me that the Z as a function of temperature, this should be less than or equal to 0. As I increase temperature, Z decreases. And as I decrease temperature, Z increases. But remember, Z is, if you look at this n epsilon, the Bose-Einstein distribution, This is 1 over z to the power minus 1 e to the power beta epsilon minus 1. This is the occupation number. And z inverse e to the power beta epsilon should be larger than or equal to 1. In fact, it has to be larger than. Even equal to is problematic. We will come to that later on. It has to be larger than 1. And which tells me that z inverse should be less than e to the power. Now z should be, if I multiply both sides by z, z should be less than e to the power beta epsilon for all epsilon, including epsilon is equal to 0, which is the ground state. Here I'm just talking about a single kind of particle, so I'm setting the ground state to 0. Which tells me that z should be always less than 1. Less than or equal to, let me say. Okay, that is one thing to keep in mind. And remember, z is e to the power mu over kt. This should be always less than or equal to 1, which tells me that mu should be less than or equal to 0. Mu is 0. Z increases if I lower the temperature. If Z increases, that means mu is increasing. But it can never, can never cross 1. Similarly, mu can never cross 0. So that is one thing to keep in mind, because we will eventually have, if I plot mu as a function of t, it will have such a dependence. It is negative. It increases with increasing temperature. Now the question is, does mu cross 0 at a finite temperature, or does it cross 0 at all? It cannot become positive, but it can become 0. That is one thing you have to keep in mind. Now let's look at the sum again. Just the sum. In fact, let me just look at one of those terms. By the way, n is, there's no minus sign over here. Let me look at this fact. Minus 1. Remember, energy ground state is 0. I only have positive energies. I don't have any negative energies. Mu is negative. Mu is somewhere over here. So if I look at that function, well, if I look at it as just a mathematical function, I can set epsilon to my negative values. I don't really care. But you see, when epsilon is equal to mu, it diverges. So there's a divergence over here. And as I increase epsilon, eventually it becomes 0 exponentially. So this is what my function looks like. And the sum, if I approximate the sum by an integral, the sum over here should be should give me the number of particles. The integral below this curve for positive energy values should give me the number of particles. Now let's see what happens if I lower the temperature, keeping mu fixed. I'm just increasing beta. I'm not changing mu. I'm not looking at the physical process. I'm just looking at this function as a mathematical function. I will eventually use these insights I gain in order to give it a physical interpretation of what is going on. Now, if I increase beta or lower temperature, you see what will change. Epsilon minus mu is positive. I'm not looking at values of epsilon less than mu. I'm only looking at values of epsilon larger than mu. Epsilon minus mu is positive. If I increase beta, that exponent becomes larger. Well, basically means that the denominator becomes larger, so my number becomes smaller. So if I increase beta, my function becomes smaller, but still it diverges at epsilon is equal to mu. So this is what it will look like at a lower temperature. Let me just say this is T0, this is T less than T0, mu fixed. But remember, the area below this curve has to be equal to the number of particles. But if I just lower the temperature, the area is now smaller. I have to increase the area somehow. Now the way to do it, just to bring the divergence closer to 0. So I have to move mu closer to 0. You see the value of my function starts increasing very fast as I go closer to 0. So I have to lower the t. If I want to keep the number of particles fixed, I have to lower the t. I cannot escape from that. If I'm lowering the t, I have to increase the value of mu. So mu should now be over here at this lower temperature, so that my function diverges at mu is equal to, epsilon is equal to mu. So this is what it will look like. What this tells me, well, basically, if you look at this region, which is the states with low energy, now there are more particles there. Well, that is what I expected. Well, if I lower the temperature, more particles will go to the ground state. Well, if I take the limit, let's say hypothetical limit, as t goes to 0. Well, as t goes to 0, that means beta starts to diverge. But then only if epsilon minus mu is close to the whatever kt. You see, if epsilon minus mu is close to kt, beta times epsilon minus mu is somewhat 1. Those states will be occupied. But if epsilon minus mu is not close to 0, but t is almost infinite, well, I won't have any particles whatsoever. If beta goes to 0, this distribution will be non-zero only if epsilon minus mu is of the order of 1 over beta, which is just the kt. But I'm taking the limit as t goes to 0. So only states with epsilon very close to mu will have a significant number of particles in them. Which basically tells me that at t equal to 0, or t approaching 0, first of all, the chemical potential should approach 0, the ground state energy. To only the states with, I will only have the particle in the ground state, and I won't have any particles in any other state. Okay? Okay, now let's go back. Okay, this exercise was just to get an intuition on what is going on. with these density of states. So if I lower the temperature, if I want to keep the number of particles fixed, I have to increase the chemical potential, mu. Mu can increase at most up to 0. It has to be negative or 0. And furthermore, in the t equal to 0 limit, all the particles will be in the ground state. I will have a macroscopic number of particles in one state only, as t goes to 0. Okay, so with this insight, let's look at this one. Let's try to calculate this one. Well, in general, what do? We have a single particles just moving around freely. I can just convert this into an integral, which the integral was, this is equal to d cubed b, d cubed q divided by h cubed, 1 over z inverse e to power beta p squared over 2m minus 1. This is my integral that I would like to calculate somehow. Well, let me look at this d cubed p, d cubed q term over there. Now, this is the q integral is the integral over position. Nothing depends on position. That just gives me a v. I can go to spherical coordinates to evaluate the p integral. That will give me 4 pi p squared dp, which will be v times 4 pi. Well, let me make a change of variables. Remember, energy is p squared over 2m. I would rather go to the energy variable, or p is equal to square root of 2m epsilon. So d cubed p, d cubed q, after integrating over the angular direction of p, the position, this becomes 4 pi. P squared is 2m epsilon v. dp is square root of 2m d epsilon divided by square root of epsilon, 2 square root of epsilon. This is 2 pi to the power 3/2 v square root of epsilon d epsilon. So this sum basically becomes 2 pi v 2m to the power 3/2 the epsilon square root of epsilon 1 over z inverse e to power beta epsilon minus 1. And epsilon goes from 0 to infinity. I have a problem though. You see, when I replaced this sum by where this g epsilon, the density of single particle states, is proportional to square root of epsilon, I also said that there is no contribution from the state with epsilon is equal to 0. Well, in general, that will be the case. There is just a single, I have almost infinitely many states. The epsilon is equal to 0 state is just one state. Contribution to anything from that single state will be almost negligible unless all my particles are within that state. So that is why I have to pay attention to the ground state, specifically to the ground state. I have to pay special attention to that. Because although it is one state which is negligible compared to all the other states, but that single state can contain almost infinitely many particles. So negligible times infinity, it can be non-negligible. So what can we do? Well, this integral does not take into account the epsilon is equal to 0 state, so let me just write it separately. It's just one contribution. You see, if you look at the first term is proportional to V in the thermodynamic limit. It seems that it diverges. The last term, well, will be negligible, unless Z is very close to 1. But we had already seen that in principle at low temperatures, Z can be very close to 1. So unless Z is very close to 1, just throw away the last term. It's negligible in the thermodynamic limit, but at low temperatures, when Z becomes very close to 1, we should keep that term. We should treat that term separately. So you see, this term is non-negligible if Z is almost equal to 1, negligible otherwise. Now that term, this is what's called, what we will define as N0. That is the number of particles in the ground state. Now let's get that integral. Well, let's just play a bit more. N is equal to 2 pi V 2m to the power 3 halves from 0 to infinity d epsilon squared. Well, let me just rewrite it. Let me make a change of variables. Let me call beta epsilon to be x salutation. Then the number of particles becomes kt to the power 3 halves from 0 to infinity dx square root of x divided by z inverse e to power x minus 1 plus n0. Well, such functions we will see quite frequently when we are studying bosons. Such functions, by such functions I mean this one. Well, if there were no minus ones over there, this just becomes the gamma function. In the case of Maxwell-Boltzmann case, this is the ordinary gamma function. So let me also factor out the gamma function. This is called G nu of Z. Just a general definition. So N is 2 pi V 2m kt to the power 3 over 2 gamma 3 over 2 times g 3 over 2 z plus n0. Now what is gamma 3 over 2? Does anybody remember?
Was it 2? 2 perhaps?
No, it definitely has a square root of pi over 2. So this is, these twos cancel. Oh, by the way, I forgot an h cubed. Because in this integral I have this h cubed. That is one factor I forgot. So this becomes v times 2m pi kt to the power 3 over 2 g 3 over 2 of z plus n0. Well, this is 1 over, if you remember that factor, that is what, in fact, why we defined the thermal wavelength, v over lambda cubed or n times lambda cubed is equal to g 3 over 2 z plus n0, n being the number density. This we have to solve. Here this is n0. Well, we can look at various cases. When z is almost equal to 1, this will be the low temperature limit. And when z is close to 0, the high temperature limit. Let's start with the high temperature limit. Z is close to 0. Now, if Z is not close to 1, since Z is not close to 1, N0 is almost 0. It is just some finite number. Remember N0, which is N0 over V, which is 1 over V, 1 Z, 1 over Z minus 1 minus 1. This is what N0 is. Well, if Z is less than 1, Z minus 1 is larger than 1, and not very close. So 1 over Z minus 1 is some finite positive number, not very large. But if I divide by V, which is a macro thermodynamic, in the thermodynamic limit, it is enormous, huge. Well, this is just 0. I can just throw it away. So n times lambda cubed should be equal to g 3 over 2 times z. This is what tells me what z is. Let's look at these functions and keep in mind, let's look at g nu functions. And let's try to find an expansion of these functions when z is close to 0. Well, this function, the definition is 1 over gamma nu from 0 to infinity dx x to the power nu minus 1 divided by z to the power minus 1 e to the power x minus 1. Well, I can expand the integrand in terms of my small parameter z, not z inverse, but z. So let me rewrite this as, let me just multiply both the numerator and denominator by z e to the power minus x. And remember, z is a small number, it is close to 0. I'm looking for a Taylor expansion of this function around z is equal to 0. Now I can expand the denominator. Which is n from 0 to infinity z to the power n plus 1 1 over gamma nu 0 to infinity dx x to the power nu minus 1 e to the power minus n plus 1 of x. That's basically the gamma function. Z to the n plus 1 divided by n plus 1. If you just make a change of variable, y is equal to n plus 1 times x, you get that 1 over n plus 1 to the power nu. And then you get what remains. The integral is just gamma nu. It cancels the 1 over gamma nu. So, well, although these functions look complicated, the Stader expansion is basically quite simple. It's just z plus z squared divided by 2 to the power nu plus z cubed, 3 to the power nu, and it goes up to infinity. So if you just keep the first term, G3 over 2 is basically z. Remember, this is what we need to solve. But that is basically z. So we know what z is. We have determined what z is in terms of n, v, and t. So z is approximately n times lambda cube. You see, you will quite often hear that, well, z is the density, or the chemical potential is the density. Well, at first order, at high temperatures, it is equal to just the density. And, well, let's see, let's find the equation of state. We should recover the ideal gas. You see, this is what I have. I can basically repeat whatever I did over here for the number of particles. I first need to write this, you see, summation over single particle stays in terms of dp and dq, etc., and converted everything to this g nu. This is basically minus let's see, d epsilon, g epsilon being the density of states, times logarithm of 1 minus z e to the power minus beta epsilon. You see, if you look at the ground state, it's just a constant. The contribution of the ground state will be just 1 logarithm of 1 minus z. Minus logarithm of 1 minus z. I'm just putting epsilon is equal to 0. And remember, 1 over z to the power minus 1, this is n0, which tells me that z minus 1 is n0, or z minus 1 is 1 plus n0. Z is this is 1 over n0, 1 plus 1 over n0, or n0 plus 1 over n0. Z is n0 over n0 plus 1. This is what Z is, in terms of the number of particles in the ground state. This is valid at any time. Now, logarithm of 1 minus Z, which is logarithm minus the logarithm of 1 minus z is just 1 over n0 plus 1, which is logarithm of n0 plus 1. in the thermodynamic limit, it is large, but it's of the order of logarithm of n. This is definitely less than or equal to logarithm of n. The first term over here, the other terms, they will be of the order of n, not the logarithm of n. So, although when I'm looking at the number of particles, I cannot ignore the contribution of the ground state. I have to take it, I have to treat it specially. But when I'm looking at calculating the Q potential, because in the number of particles, the contribution of the ground state can be of the order of n. But when I look at the Q potential, the contribution of the ground state is at most logarithm of n, which is negligible. So I can just throw it away. I don't need to worry about that. Now let's look at this term, and remember G epsilon is proportional to epsilon to the 1/2. Now what I will do is, I will do an integration by parts so that I can get rid of the logarithm. So G epsilon is basically derivative with respect to epsilon of G epsilon times epsilon. Remember, G epsilon times epsilon is epsilon to the power 3/2. So if I take the derivative, it gives me a 3/2 factor. So let me also add this 2/3. Now, what does this tell me? PV over KT. This is equal to minus 2/3 d epsilon d by d epsilon G epsilon times epsilon logarithm of 1 minus z e to power minus beta epsilon PV over K, which is equal to minus 2/3. Well, if I do an integration by part, if you consider the boundary terms are when epsilon goes to 0. Well, the logarithm becomes 0 at that boundary. The other limit is when epsilon goes to 0. In that case, G epsilon times epsilon goes to 0. So I don't have any contribution from the boundary terms. The remaining term is the epsilon, G epsilon times epsilon, derivative with respect to epsilon of the logarithm, which is 2/3 d epsilon G epsilon times epsilon. The derivative of that logarithm will just give me z inverse e to power beta epsilon minus 1. Well, if you note, if you compare it with our previous result, PV over KT to this one. Well, in our previous result, we had this was equal to V over lambda cubed G 3 over 2 Z. I will basically use the same result. This is equal to, well, there's no minus sign, 2/3. I will get V over lambda cube. There will be, and due to this epsilon, I will get an additional 1 over beta. Remember? No. Remember when I converted it into this expression, I defined y is equal to beta epsilon. Or epsilon is equal to y over beta. Now there's an additional epsilon, so I get an additional 1 over beta. What will remain will be g, not 3 over 2, but 5 over 2 z. But g 5 over 2 z has a 1 over gamma 5 over 2, whereas the other one had gamma 3 over 2. you are lost. Okay, trust me with this result, then PV over KT, this is, well, this is just 3 over 2 V over lambda cubed times KT G5 over 2 of Z. Well, V's cancel. P.
Üçte sadece orası?
Where?
Gamma.
Gamma 5 over 2 is 3 over 2, gamma 3 over 2. So it cancels the gamma 3 over 2 in the denominator. I have 2/3 over here, a 3 over 2 over there, they cancel. P over KT is KT over lambda cubed, G5 over 2 of Z. I'm not so sure about this KT, by the way, I didn't like it. And we had just known what G5 over 2Z is. This is approximately Z, because that is what we had derived. G nu of Z, it just starts with Z. And Z is n times lambda cube. These lambda cubes cancel. We have n KT. As I said, I don't like the KT in the front. Okay, I missed a factor of KT somewhere in my derivation. And I think I know where I missed it. You see, the derivative of this logarithm with respect to epsilon brings down an additional factor of beta. Yes. You see, this derivative with respect to epsilon, I have Z times e to the power minus beta epsilon times beta over there. So here there is a beta divided by whatever is inside the logarithm, so these betas basically cancel each other. So we have PV is equal to NKT. So we did recover the ideal gas law for the Maxwell-Boltzmann case. Now, if I collect some of the results that we had derived, okay, one is this one. This is true for any Z, for any temperature. For this system, this has to be satisfied. Another equation we obtained is this one. This also has to be satisfied whatever the temperature is, whatever the value of Z is. And we also know that G nu of Z is Z plus Z squared over 2 to the power nu plus Z cubed to the power over 3 to the power nu, etc. Now we did recover the ideal gas equation of state, but we can do better than that. We can calculate the first correction to that. I will not do it today, but basically what we will have is n lambda cube is equal to Z plus Z squared to the power 2 to the power 3 halves From here we can solve for Z. And once you know the value of Z, P over KT will be 1 over lambda cubed G Z plus Z squared divided by 2 to the power 5 over 2 and obtain the first correction. So that will give us the first correction to the pressure. We will see that the pressure will be a bit smaller for bosons. Well, that's kind of expected, because if you remember what we had when we looked at a two boson system, we said that if they are bosons, effectively there's an attractive potential. Well, that attractive potential just lowers the pressure that our boson system exerts on the walls. And here we will also recover that. Well, we will do that on Wednesday. We have a lecture on Wednesday. So any last questions? You see, the trick will be, it's basically straightforward. We have this equation, which we need to solve for Z. And once we determine Z, if you put it over here, you get the pressure. Well, we can, if you look at this expression over here, PV over KT, this is what we derived. Or PV is equal to 2/3 d epsilon, g epsilon, epsilon, and Bose-Einstein of epsilon. But that integral is nothing but the total energy of my system. You see, that integral over epsilon with the density of states is nothing but some summation over the states. Summation over single particle states. Epsilon is the energy of a given state, and n of epsilon is the number of particles in that state. So this is essentially 2/3 n epsilon I. So PV is 2/3 times U. You see, this is valid at all temperatures, whatever the value of Z is. Again, when I'm calculating the energy, I don't need to pay special attention to the ground state, because ground state has zero energy anyway. No matter how many particles I have in the ground state, it doesn't contribute to the energy. Only in calculating the total number of particles, I have to pay attention to what happens to the ground state. Basically, because although it's just a single state compared to infinitely many states I might have, I can have almost infinitely particles in the ground state. So any questions? So anybody still has some energy to ask a question?
Benim daha önceden bir soru var. Bu mesela başta degenerate olan state'lerden başlayıp sonra degenerate olmayan state'lere nasıl geçiyoruz? Ben bunu anlamadım.
Where?
Normalde mesela işte firm statistiği falan incelerken her bir state'in degeneracy'si var. GI'lerle başlamıştık.
You mean in the derivation?
Yes.
Of the distribution? Okay, so what we had done was, we have all these almost degenerate states. We first divided these into cells. Is this what you're asking?
Mm-hmm.
So in each one of these cells, I have GI states which are almost degenerate. And we said that, okay, let's have Ni particles in this state. So we calculated the most probable value of Ni, and we said that, okay, let's denote it by Ni star. And for the most probable values, Ni star over Gi had to be equal to 1 over e to power beta epsilon minus mu plus A, or minus A. This was our general result. So we didn't calculate Ni's. What we obtained was Ni star over Gi.
So we then go basically over. So we basically sum over all cells instead
Yes.
of the
Individual. No. Yeah. So, and then we said that, okay, if GI states each have n I star particles, n I star over GI will be the average number of particles of each one of those single particle states. Because since they all have the same energy, there is no reason why one should have more or less particles than the other one.
But still, the total number of particles is restricted to n, right?
Yes. Yes, yes.
But when we sum over n equals from n equals 0 to infinity.
No. Okay, let me clarify this. When I say ni is equal to n, this is in the microcanonical ensemble. This is in the microcanonical ensemble. And we had all these cells and calculated the most probable distribution, etc. But then we went to the grand canonical ensemble. Where this sum over ni is gives us the average number of particles. Well, the number of particles in the grand canonical ensemble can be infinite. The probability of me having infinitely many particles in my state will be negligibly zero. But still, in principle, there's nothing that prevents me from having infinitely many particles in my system, because this number is not fixed. So that's a different ensemble. So in fact, that was the simplification of the grand canonical ensemble. I don't need to impose this condition. Or even this condition, I don't impose it. But what I do is I introduce a parameter mu. I choose mu such that the average number of particles is n bar. This equation basically defines mu. Or not defines, determines mu. But in the grand canonical ensemble, the number of particles is not fixed. But at the end of the day, we basically get the same answer whether we do the microcanonical ensemble or the grand canonical ensemble, unless we are close to a phase transition. Okay, so see you on Wednesday.